So hello everyone, welcome back. So in today's video, we'll be taking up a problem from mechanics. So a very similar problem is also there in Pathfinder. So at the end of the video, I'll just give you guys that problem as homework. Okay. So let's read the problem. So it's given at the edge of a hemispherical bowl whose radius is r, a weightless thread whose length is r by 2 is fixed. Okay, so this is the thread that they're talking about and its length is half the radius, to the second end of which a small body is attached. The body is held on the edge of the bowl so that the thread is stretched. At some point in time, the body is released, so we have to find the velocity and acceleration of the body at the moment when it passes the lowest point on its trajectory. Okay, so the ball will move in a trajectory something like this, right? So when it reaches the bottommost point, we have to find its speed and its acceleration. Okay, so that's the question. So give this problem a try, guys, then check out the solution. Okay, so first let's draw a top view of the situation. So let's give this point the name A, and I'm going to name the ball as B. So let's say the point A is over here and this is the point B where the mass is present. Okay, so basically this is the top view of the situation. Let's say this is the center of curvature of the hemisphere. So if I connect it to the point B, this distance is r, this distance is r by 2, and this distance is also r. So let's call the center as C. Okay, so the first idea here is that the distance AB and the distance BC are constants. Why? Because the end, this length AB is the length of the string, right? That is going to be a constant throughout the motion. The string is not going to slack, right? So the distance AB is going to be a constant and it is equal to r by 2. And the distance BC will also be r because the point, however it moves along the sphere, it is going to move on the sphere, right? And if it is moving on the sphere, it is quite obvious that the distance from the center of the hemisphere to any point on the hemisphere is equal to the radius, right? So the distance BC therefore is equal to the radius of the hemisphere all the time. It not just when the ball is up here, at any point on the mass's trajectory, its distance from the center of the hemisphere will be equal to the radius r. From here we get a constraint that these two distances have to be constant in terms of magnitude. So basically, mathematically speaking, we can say that this point B will move in a trajectory such that its distance from A is r by 2 and its distance from C is equal to r. So we can kind of use distance formula here. So let's say the coordinate at any general time of the point B is xyz, and let's say the origin is point A. So the distance AB using distance formula is x squared plus y squared plus z squared, and this would be equal to r by 2 squared. Right, now we can use the second constraint that the distance BC is r. So the point C is going to be r comma 0 comma 0. Right, if this is 0 comma 0 comma 0. So I'm assuming this is the x direction and I'm assuming this is the y direction, and z direction is out of the page. Okay, the distance BC is going to be x minus r the whole squared plus y squared plus z squared equals r squared. So basically the point B satisfies these two equations at all times. So now what can we do? We can subtract these two equations, right? And let's see what we get. Okay, so once you subtract this two and subtract these two equations and after solving of it, we get x equals r by 8. So what that means is the particle B actually moves in a plane such that its x coordinate is always fixed, and it is equal to r by 8. So basically the x coordinate of the particle B is actually a constant throughout the motion. So basically from the top view, basically x equals r by 8 will be somewhere over here, right? So if you slice the hemisphere along this x equals r by 8 point, the particle B will always lie in this plane. So now for the exact trajectory, what we can do is we can take this value of x and put it into this equation over here, and we get y square plus z square equals some constant squared. So this is the equation of a circle, and the plane of the circle is in the YZ plane. So now let's try to draw the YZ picture, or basically the side view of the situation. So y-axis was in the upward direction from in the top view. So in the side view, it will be in this particular direction, and this was the z direction. Okay, and in the YZ plane, the trajectory of the particle is a circular motion, meaning the particle B will move in a circle of radius root 15r divided by 8. Okay, so this is the radius squared. So the particle B from the YZ picture will move in a circle whose radius is root 15r by 8. Okay, so if I draw a slightly different view, let's say this is the particle, and once we release the particle, what will happen is it will move along this circle. Okay, and this circle is in the vertical plane. So the particle, once we release it, it will move along this trajectory, right, which we determine it is a circle whose radius is root 15r by 8. Okay, and the center of this circle lies over here. Okay, so now we can also visualize this geometrically. So basically these are the equations of two spheres, right? So the intersection of, two spheres will give us a circle. So basically if you want to model this like a math problem, it is basically going to be, there are two spheres and the particle actually moves along the common intersection, along the curve that is the intersection of these two spheres, so which is actually a circle. Okay, that's the main idea of this problem. The particle is going to move in a circle in the vertical plane. Okay, and the radius, and another thing that is important is that the radius of this circle is root 15r divided by 8. Now once we know this, we are well equipped to write the answers to all the problems. So in the question we were asked, what is the velocity when it is at the bottommost position? So from the YZ view, it is the particle will be over here, right? So basically the particle has dropped by the distance root 15r divided by 8, right? So its velocity is just going to be root 2gh, right? We can just directly write it using energy conservation. So this is going to be square root of 2g times the drop in height, which is root 15r divided by 8. So the speed at the lowest point is going to be square root 15 gr divided by 2. So now let's talk about the acceleration. For the acceleration, if we observe the path of the particle, it is moving in a circular path, right? So if it is moving in a circular path, it will have two accelerations. One is the normal acceleration, right? And the other is the tangential acceleration. When it is at the lowest point, it won't have any tangential acceleration because there is no tangential force, right? There's no force in the tangential direction. There is no friction present or air drag, none of that. So tangential acceleration is just going to be 0 in this case. But as the particle has some speed, right? Its speed is actually v. It will have a normal acceleration that is directed towards the center of the circular motion, or the center of curvature that we can call. And the center of curvature is the center of the circle in which the particle is moving. So from this view, the center actually lies over here. Okay, so then the magnitude of the centripetal acceleration or the normal acceleration is going to be speed square divided by the radius of curvature. So, and here the radius of curvature is root 15r divided by 8. So if we just substitute all the values in, we get the answer as 2g. So the normal acceleration at the bottommost point is 2g in the z direction. So we can just write it as 2g z cap. Okay, so these were the two problems that were asked to us. Okay, so now the thing is, let's say this is my fixed point A, okay, and this is where the mass is present. Okay, so if I join a line to the center of the hemisphere, this forms a side view of the situation. So the xy is the top view, zy is the plane of the circular motion. So this view is going to be zx, right? So this is basically the z direction and this is the x direction. So this is going to be the zx view. So in this view, we can see that the tensile force on the rod is going to be in this direction towards A, and the normal force is towards the center of this hemisphere. And if you guys remember, the x coordinate is fixed, so I'm just going to demarcate it with this dotted line. So this dotted line is that plane along which the particle is moving. Okay, and this distance was actually equal to r by 8. So anyway, the reason I am discussing this is for the homework problem. So okay, so now I'm not going to give you any more hints. Okay, so basically you know where the acceleration is directed and you know all the forces acting on the particle. Now you can find the tensile force, which is what is asked in this question. So this question is CYU 16 from Work Power Energy, okay, from the Pathfinder book. So in this question, the difference is that they want you to find the tensile force in the rod when it is at the lowest point. Okay, so yeah, give this problem a try. And if you want any help, you can just comment down below. I'll help you out. So that's it for this video, guys. If you enjoyed the video, make sure to like, share, and subscribe. And that's it. Thanks for watching.